there's a couple of things that I need to make sure that we're doing correct on here. So let me do this, just run through that derivative real quick again, and everything that we need to know on that. So we have, oh, come on, don't do that. Okay, so we have f of x equals cosine of x squared. So I'm going to do the derivative real fast here again. The equation solving and the identity is sometimes what bothers students on this, but I want to show you a different way to solve this equation. So we said the derivative was 2 cosine x, then we had to do the derivative of the inside part, and we got 2 cosine x, and then the derivative of the cosine is negative sine x, so I'm going to put the negative there. So anyway, what we had is the derivative was negative 2 sine x cosine x. Okay, now you guys, that shouldn't be a problem, right? That's pretty basic chain rule derivative. Now the thing on this is when you do your sign chart, you got two ways to do this. Now you can also pull out the identity, and again, we said that negative 2, or we said 2 sine x cosine x, we had an identity for that, and that's the sine of 2x. And that identity shows up quite a bit. So I'm going to write this as negative sine of 2x. Okay, so I'm going to highlight this derivative and this derivative. When we're doing the sign chart, we have to use one of those two. Okay? When I solve the equation, I can divide by a negative when I set it equal to 0, and that has no impact. But disregarding that negative has an impact on the sign chart. So I want to make sure that you got that okay. Let me show you kind of the way that we typically teach how to do trig equations when they have period changes. So what I'm going to look at is I'm just going to take negative sine 2x equals 0. And yeah, you can divide both sides by negative 1. There's not a thing wrong with doing that when you're solving this equation. Okay? So let me go back and see if this makes sense. Now, like, this is the way I typically teach this kind of an equation in a trig class. What you can do is you could take the inverse sine of both sides of this equation. You guys probably should write this down right here. If you got any room to squeeze it in, because I'm thinking you might understand it better this way than what I did before. So you can actually just take the inverse sine of both sides. Okay? Now, you guys remember if I do the inverse sine of the sine of 2x, what you get?
2x.
2x, exactly. Okay. Now, if you were to go to a unit circle, this is where your unit circle comes into play. There are two places on the unit circle where the sine is equal to 0. Where is that?
0 and pi.
0 and pi. Okay. So you have 1, 0, because of course you remember the sine is equal to the y value. So you basically got 0 radians and you got pi radians, okay, like that. Now, what I'm going to do is I'm going to write this then as 2x equals 0 plus the period. What is the general period of just a basic sine wave, sine x? What's the period?
2 pi.
2 pi. So let's put 2 pi k. Then let's do 2x equals pi plus 2 pi k like this. Okay, you may remember this, you may not. This is one of the harder types of trig equations that we teach in a trig class. Okay, so I'm just saying, okay, the sine is equal to 0 at 0 radians and pi radians. Then I can divide both sides of this by 2. So what I get is I get x is equal to 0 plus pi k, where k is an integer. Okay, that would be one solution. Okay, then this one I can divide by 2. And I get x is equal to pi over 2 plus pi k, where k is an integer. Okay, does that look familiar to you guys at all? I'm just curious. I mean, it's easy to forget stuff. Okay, but that's kind of usually the technique that I like to teach if you're doing like sine of 2x, sine of 3x, where there's a period change. Okay, now, you already know that, like, if you had sine of 2x, what's the period, or how do you find the period of sine of 2x? What's the formula? 2 pi over b, right? You guys remember that? Okay, so that's pi. See how that was incorporated in my answer? Every time pi goes by, you have the same answer over and over again. So see those critical points. are right there. The formula's already there, so you don't have to quite do maybe as much analysis. So what we could say for our critical points is we could say this is really given x equals pi k. Okay, so every time pi k goes by, you have a critical point, and then this is really saying pi over 2 plus pi k. Okay, and you could write both of those. It's just that they're unnecessary. So you could write, if you wanted to, x equals pi k, where k is an integer, and then you could write x equals pi over 2 plus pi k, where k is an integer also. And there's nothing wrong with writing it that way. It's just every time pi over 2 goes by, you're going to get the same 0 anyway. You're going to get a 0 anyway. Okay? So we got that. So if you understand from your background how to solve that equation this way, that might help you a little bit on some of these problems. That's my thinking. Anyway, what do you think? I didn't really have to look at the unit circle as much. So now what I'm going to do is we're going to do our sign chart. Now we've already done the sign chart, but I just want to make sure that we have one thing down on this correctly. I'm not sure if I was doing that quite correct when I was doing this before. I may not have been looking at the derivative the wrong way. So basically our test points are pi, we're going to break this up into 0, pi over 2, so 0, pi over 2, like we did before, and then all the way up to pi. Okay, so that's all we need to know on this. And the thing is, you should have a good enough trig background that doesn't a sine wave just increase, hit a max, and then start decreasing? Okay, so it's just going to kind of, from the minimum, it's going to go increase to the max, decrease to the min, and then let's start over again. So it's just going to go increase, decrease over and over again forever. So if you can break up your interval into two parts, then you should have exactly how it goes forever. Does that make any sense? Okay, so let's do that one more time. Now what we're doing, and I'm not sure if I did this before, we're going to plug into either this or this. I'm just going to plug into -2 sine x cosine x. Now that negative needs to be there in this sign chart. I'm not sure if I did that when I was doing this problem before. I don't remember. But take a test point. It can be bigger than 0, between 0 and pi over 2. And I don't care what it is. What if we just said 0.1? Isn't 0.1 in quadrant 1? 0.1 radians in quadrant 1, right? That's all you care about. So if you did like, and just think of it this way. This is quadrant 1, and between pi over 2 and pi, isn't that just quadrant 2? So who cares about test points? You could just say, okay, the sine of a quadrant 1 angle is what? Positive or negative? What's the trig function of every quadrant 1 angle there is? It's positive, isn't it? So that's positive. What is the cosine of a quadrant 1 angle? Positive. So what do you have? Negative times positive times positive. So it's negative. So that means that you're decreasing. Now, I think I wrote the interval right, but you can tell on here that that's decreasing, right? Okay. Then here, the best way to do this is, hey, this is quadrant 2. So you have -2. Now, if you're in quadrant 2, is the sign positive or negative? What if you forget? The sign's y over r. Y is positive in quadrant 2, so that's a positive. Okay, how about the cosine? If the cosine's quadrant 2, cosine's x over r. What is x in quadrant 2? It's negative. So look what you have. You have a negative times a positive times a negative. That's a positive, so that means you increase. Now, isn't that easier to do it that way? Okay, because it's all about quadrants anyway. Okay, so if you can just reason out that this is quadrant 1 from 0 to pi over 2, that's quadrant 2, then you can figure it out pretty easily that way. That's probably the optimum way to analyze that sign chart on that problem. And then basically what you would have, if you were going to do like increasing, you know, you can clearly see how that goes on the graph, and that's just a matter of writing the intervals out. Typically all I have students do is, like I showed you before, is like this. You can just write a couple of intervals out. So you could say like this is negative pi over 2 to 0. So you could say it's increasing from negative pi over 2 to 0. Then it picks up again from pi over 2 to pi. And then so forth like that. Okay, typically on a problem like this, I'm more likely to give this, tell you what interval I want you to describe that on. And then decreasing would be you could say, just pick a couple of intervals and name them, and then just kind of name the pattern like this. So I'm going to say, like, this is negative pi. We would say, like, negative pi to negative pi over 2. Whoops. Okay, union, and then 0. Then decreasing is going to be from 0 to pi, like that, and so forth. Or 0 to pi over 2, and so forth, like that. Okay? Okay? Now, these are the kind of problems that probably in this section that you're probably going to have the most challenge with is stuff like logarithms and trig functions. Not so much polynomials. Okay? So that's the idea. Get your graphing calculator out to reason through and kind of help you. I just wanted to do mainly the solving of that and just kind of show you a different approach to that. Okay? And then when you're doing sign charts on trig functions, think about quadrants. That'll help you a little bit. Okay, so we're going to move. I wanted to just kind of talk about a couple of graphs, and I want to get to the concavity and kind of finish up that. This is a real long section. It's got a lot of stuff. But like I said, it's probably the biggest, most important section in Chapter 4 because it has all of the fundamentals of what a derivative really is and what it means. So I'm going to go ahead and move to the next page and just kind of go over a couple of things real quick. I just put a couple of graphs on here for interpretation. But the key thing is, and we've already kind of talked about this, if you have a local minimum, what's happening on a function is that you're going to have a function that decreases, then starts increasing. Okay, now you got to be continuous function. It's going to go from decrease to increase. Then if you have a local maximum like you have on this, then what's happening? The derivative changes from being a positive derivative to a negative derivative, which essentially just says the function's increasing, then it starts decreasing. So when we do sign charts, we can also use that to analyze whether we have local maximums or local minimums. So that's the next thing I'm going to begin to look at here then. Okay? Okay, so let's go down this example 1. I'm going to show you what we mean by the first derivative test. And I'm going to do, this is a polynomial, so it's not too hard to do. So if you're doing the first derivative test, what that really means is you take the first derivative and find the critical points, and then you analyze the sign in a sign chart. Okay, that's what this is really saying. So I'm going to go ahead and start with, I'm going to do this kind of at the side, and let's go ahead and do the first derivative. This is a polynomial, so it shouldn't be too bad to do. So this is going to be 10x to the fourth minus 20x to the third minus 30x to the second. That'll be our first derivative. Now that derivative is always defined. It's a polynomial, so f prime of x is never going to be 0. We don't have to worry about where it's undefined. But what we do need to do is we need to go ahead and take this derivative and we need to set this equal to 0. Okay, when we do this then. Okay? Now, do you have any constants that you could divide out to make the factoring simpler? You can divide by 10. Okay, I think it's good to divide by 10 because it just gets rid of that. Doesn't make any difference. Now, you don't want to divide by variables, but it is okay to divide by constants that are common factors. It makes the factoring simpler. So this is x to the fourth minus 2x to the third minus 3x squared equals 0, like that. Okay? How do you factor this? You take x squared out. Good. Okay, so you're going to take that common factor out. So that's going to leave x to the second minus 2x minus 3. Okay, then it looks like we can factor that trinomial one more time. So when I factor this trinomial, let's see what we get on that. That's going to go x and x. You're going to have 3 and 1 to get 3 with a minus and plus like that. Okay, so we're going to have critical points are going to exist where x squared is 0, where x minus 3 is 0, and where x plus 1 is equal to 0, like that. Okay, so polynomials, usually students do pretty well with polynomials if the factoring is under control. So what are the 3 critical points? 0, 3, and -1. Okay, just do it in your head. You don't have to show the steps on these. You can do this in your head. So x equals 0, x equals 3, x equals -1. So let's just write down in our blank, it doesn't matter what order. I'm going to put these in order, -1, 0, and 3 like this. Now what we're going to do is we're going to find local min and max. We're going to apply the first derivative test to find that. And that's what the first derivative test does, is you use a sign chart to analyze where the local max and mins are. Okay? So far okay? Okay? That's an easy derivative, and then the algebra shouldn't be too bad on this. I sure hope not. Okay, let's make a sign chart. All right, so what we want to do is want to divide this up in order. A lot of times I see students do this way out of order. Okay, you want to have, x equals -1. That's a place where the derivative is 0. X equals 0, and x equals 3. Okay, now we're going to plug into the factored form of the derivative, and I'll show you a couple of little ways that you can simplify this too. Now again, with a little practice, you can do this in your head. You'll see what I mean on these kind of problems with polynomials. So let's take a test value less than -1. Let's take like -2. Now, see if you follow what I'm doing. Okay, now if I plug in, if I square a number, what am I always going to get for this first factor? Isn't x squared always going to be positive? On all these test points, it's going to be positive. So what I'm going to do is, see, we got 3 factors. We might as well right now just kind of write down the 3 factors. I'm going to try to do this a little bit more in my head this time, and just tell me if you see if you follow what I'm doing. So the first factor is always positive, isn't it? Because it's x squared. Don't waste your time, okay? It's positive. No matter what test point you plug in there, you're going to get a positive. Now, let's plug in -2 into -2 minus 3. What's -2 minus 3? It's negative. What's -2 plus 1? Negative. You guys see what I'm doing? Do that in your head. -2 minus 3 is negative. -2 plus 1 is negative. Positive times negative is positive. So that means the function increases. Okay, you guys okay with me just doing that in my head? You do the same thing. Okay, I don't care. Okay, now let's take a test point between 0 and -1. Well, how about -1/2? Don't worry that it's a fraction. It's not a big deal. So what would you get if you did -1/2 minus 3? You get a negative or positive? You get a negative. That's all you care about. How about -1/2 plus 1? Positive. Now you have a positive times a negative times a positive. That's negative. That means the function's decreasing. Okay? So just, if you can do it in your head, do it. Saves you time, that's for sure. Okay, now let's take a test point between 0 and 3. Let's take 1. Okay, so if we replaced all of these x's with 1, we're going to have 1 minus 3 is negative. 1 plus 1 is positive. So we have a positive times a negative times a positive. So that's going to be negative. So that means the function's going to decrease. Okay. Now take a test point bigger than 3, like say 4. Okay, again, doing this all in your head. If you plug a 4 in for x, what do you have? You have positive. 4 minus 3 is positive. 4 plus 1 is positive, so what do you get? Positive, so it's increasing. Okay, you guys see what I'm doing? I'm not going to take a lot of time on the details of the arithmetic, because what I just did is arithmetic. And I plugged it into each of those factors. So what we're going to do now, we're going to go ahead and write down our intervals for increasing and decreasing. Okay, so what we have is increasing, we ended up being in these 2 places. So let's write an interval for that. That's going to be -infinity to 1, union 3 to infinity. Okay, then decreasing, we kind of got 2 places, but you do have to separate this into 2 places. Okay, you can't just make it go from -1 to 3. So on decreasing, what we're going to say is we're going to say -1 to 0, union 0 to 3 like that. Okay? Now, the first derivative test basically tells us that based on this sign chart, we can tell where we have minimums and maximums. So one thing that you could kind of do on this, and I'm going to just kind of do this. You can kind of reason this problem out like this. Okay, what's going on? I'm increasing. I'm going to take this orange marker. I'm increasing, right? Then what happens? I have to change directions, but then I'm decreasing. Why am I leveling off? Because the derivative is 0, right? Then I start decreasing again. Then I start increasing again. Okay, so what's happening on this is I'm increasing, decreasing. This thing really levels off. I didn't do a very good job of writing that. The graph is doing more something kind of like this. So what this means is, what is that point right there going to be, a max or min? That's a max. Okay, what is a max? By the first derivative test, it's a place on the graph where the function changed from increasing to decreasing. Okay, how about this point right here? Is that going to be a max or min? No. Okay, how about this point right here? That's a min. So what the first derivative test is saying is it's where the derivatives have a sign change. And notice that x equals 0, the derivative did not change sign. It was just always negative. So that means it cannot be a negative or positive. So what we're going to do on this is I'm just going to name these with x values. So we're going to say we have a max at x equals -1, and we're going to have a minimum at x equals 3. Like that. That's it. That's what the first derivative test does. It tells you increasing and decreasing intervals, then you can use that to tell where you have maxes or mins. Okay? Does that look okay? Okay. If the derivative is pretty easy, you'll probably do fine with these problems. It's the ones where you get into trig and exponentials and those kind of things where they get harder. Okay, that's just the algebra part that goes on. Okay, any question with that? Okay. All right, let's look at this one. This has a little, these two right here are going to have derivatives a little bit more difficult. So we're going to do first derivative test on these. Okay, so let's go ahead and let's work on the derivative for f prime of x here. Now, you're going to have to use a product rule on this. This is a product of two functions, so we're going to say the first, x to the 2/3, times the derivative of the second. And you can do that in your head. You don't have to write the first step necessarily. I think it's a good habit, but you don't have to. So times the derivative of the second like that. So we're going to go ahead and crunch that out. So we're going to have the first is x to the 2/3. The derivative of x minus 5 is 1. Then we have x minus 5. Then when you do the derivative of x to the 2/3, that's a power rule. So that's going to be 2/3 x to the 2/3 minus 3/3. You can do that in your head if you want to. So this is going to give x to the 2/3 plus x minus 5 times 2/3 times x to the -1/3 like that. Okay, now I think it's important on this one to go ahead and change this negative exponent to positive, okay, because that'll help you kind of understand where the first derivative might be undefined. So I'm going to write this as x to the 2/3 plus x minus 5 times 2 over 3 x to the 1/3 like that. Okay, and we'll stop kind of at the derivative on that. Okay, now when we do critical points, we have to do two things. Okay, first thing we got to do is figure out, is this derivative that we're done with now, is this thing right here ever undefined? Is there any value of x that would make that expression undefined? There's something that's staring me right in the face. Zero, right, okay. The thing is, if you look at this piece right here, okay, if x is equal to 0, what do you have? You have 0 to the 1/3, which is 0, right? 0 to any power is 0, so you would have a 0 undefined. So you would have a critical point at x equals 0, without a doubt. Remember, critical points can be where derivatives are undefined. You are undefined right there because you have 2 over 0, right?
Okay. Would you add the x to the 2/3 to that? So
doesn't matter. And if you did that, you would still have that in the denominator anyway, but it doesn't matter. I mean, we've done the derivative, so we have located a place where it's undefined, okay? All right, so we got that. Now what we need to do is, that's one critical point. We need to see if we set this equal to 0, what's going to happen. So that's what I'll do now is just write down this derivative. X to the 2/3 plus x minus 5. Let's just write it like this again. And let's set this equal to 0. Okay, let's go through and solve this equation. Now, this is where students get into problems, is how in the world do I solve an equation like this? Well, first of all, general rule of thumb. Go ahead.
Never mind. I got it.
What's
I
that?
got it. I got it.
You okay? All right. General rule of thumb. You have an equation with a fraction in it. What do you want to do if you have an equation with a fraction in it? Get rid of the fraction. Okay? So if we multiplied both sides by 3x to the 1/3, we would get rid of the fraction. And this is one strategy. This is what I'm going to do. Is just multiply both sides by that, and then that will get rid of the fraction. Okay? So watch carefully. Let's see how on top of the algebra we are here. Okay? So what are you going to do with the exponents on x to the 1/3 times x to the 2/3? You're going to add them. What's 1/3 plus 2/3? It's 1. It's 3/3. So this is going to be 3x to the 3/3, or 1. That's x minus 5 is going to come down. And see, when you multiply that out, that's going to cross that out, leaving you a 2. And this side right here is going to leave you a 0. Okay, like that. Okay, so I'm just doing a distributive property, and I canceled out that fraction. So what I've got now is I've got 3x plus, and I'm going to do a distributive property here, so I'm going to have 2x minus 10 equals 0. So I end up having 5x minus 10 equals 0. So now you can solve that pretty easily in your head. What is the answer to that in your head? X equals 2. Okay, you don't have to show all the details, so that's another critical point, x equals 2. Okay, tell me if you understand that algebra. It's like you've already seen, that's what you get into calculus. You get into stuff that you haven't seen before. You've learned the principles behind this stuff, you just haven't seen it before. So I got rid of fractions. That's generally what I'm trained to do if I see an equation with fractions. Okay, does that look any good? Okay. All right, sign chart time. Okay, so we're going to do this. Okay, so let's make a sign chart here. Okay, so what we have is we have x equals 0. And remember, the derivative did not exist there. You're going to find you have a cusp on this. You can look at the graph I already gave you on this and see the cusp there. Then you have x equals 2, okay, like that. Okay? Now, this kind of a problem right here, you just kind of have to sort of crunch out the details, and you just have to plug in test points. You could use your calculator, certainly, to help you with this kind of stuff. So I'm going to write down the derivative. We could have put this in a factored form too, so I'm going to, actually, I'm going to do something on the board here, because I don't have a lot of room on here. So if I put this in a factored form, I mean, you can plug into that derivative right now if you want to, but I'm kind of thinking if we took this thing in the original form, x to the 2/3 plus x minus 5 times 2/3 x to the negative 1/3, if we did this in a factored form, the common factor is the one with the lowest exponent. So that's x to the negative 1/3. You would have to multiply this by x to the 3/3 to get that. And then this would be plus 2/3 times x minus 5. Okay, and just prove to yourself that that's right. Negative 1/3 plus 3/3 is 2/3, right? And then this times this will give this expression right here. So you would end up having x to the negative 1/3 times x. And then this part right here would just be 2/3 x, and then minus 10/3 x like that. I don't know if that'll help us to analyze our sign chart any easier or not. It was just kind of a thought that I had. So let's go ahead and just take some test points, plug them in. See what we get. This is a kind of thing like this too, is instead of getting bogged down in a lot of arithmetic, let's just kind of plug in and see what we have on there. So one thing you're going to find is if you did like this form of the derivative or the factored form that I have on the board, without going through the details, I don't want to get bogged down on all the details of this arithmetic. I don't mind on some of the more complex functions you encounter in homework that you look at the graph, okay? Because isn't this graph going to tell you what the sign chart is anyway? What is the derivative going to be right here? In this part right here. Below 0, what kind of derivative do you have? Yeah, positive. That's what the sign chart's going to give you if you crunch out. If you plug that test point into that derivative and go through the details, that's what you're going to get, okay? And then what is the derivative going to be from 0 to 2 based on my graph? Negative, okay? So it's going to be negative like that. And then what's it going to be past 2? Positive. I want you guys to know that. I want you to be able to look at a graph and tell what its derivative is. So it's going to go like that. So what you would have then is you would end up having the function increasing here, decreasing here, then increasing again like that, okay? So if you're doing, any kind of a graph that's a little more complex with the arithmetic of the sign chart, get your graphing calculator out and look at it, okay? I don't mind you doing that. So what we would have on this then is the graph is basically going to do something kind of like this. Now, usually what I tell students to do is once you get your sign chart, then just kind of analyze what's going on. Now, what's happening on this is when x is equal to 0, you actually have a y value. Like if you plugged in x equals 0, 0 minus 5 is 0, 0 times this function is 0, you actually have a function value. But what you don't have is a derivative. So what this is going to mean is that this thing is going to have a cusp. So it's going to decrease like that, and it's going to hit that low point and go like that. So that sign chart tells you the roughly how that graph goes. So where are you going to have a maximum? You're going to have a maximum right there. So you're going to have a local max at x equals 0, or local max at x equals 0. Then you're going to have a local min there, which is going to be x equals 2. Then you can name your increasing and decreasing intervals. So this thing is going to increase 2 places, the 2 things are highlighted. So we write that as negative infinity to 0, union 2 to infinity. And then we say the function decreases from 0 to 2. Okay?
So even though that's a cusp, it's still a local max?
Yes, cusps can be local maxes or mins.
Yes.
And by the way, the reason I knew, without looking at a graphing calculator, that was going to be a cusp is because if you plug in x equals 0 into the function, you get an answer. If x is equal to 5 in the function, you get 0. You get a 0.00. So there is a definitive point there.
And it's continuous.
Yes, and it's continuous. Therefore, it's going to have to be a cusp. It can't be an asymptote.
Yeah.
Can't be a break in it either. The only place this function is always defined. Now, if you look at the original function, it's continuous everywhere. So that's how I know it's got to be a cusp. Okay? Okay, how's that look? Hardest part of that, what the hardest part of that problem is? The sign chart with the arithmetic. Okay, and if you get into that, just get your graphing calculator out. Doesn't make that much difference to me on those kind of problems. Okay? Save yourself time too. I mean, you're doing your homework. If you're doing the first derivative test, I want you to do a sign chart, but speed that process up a little bit. You see what I mean? Okay. All right. If it's a polynomial or something that's pretty simple, then do it, because that's the kind of thing I test you on more so. All right. So let's go ahead and do this example 3, and then I want to finish up here with talking just a little bit about concavity. Okay. So. All right, we go to this thing. Okay, we're going to do the first derivative of this. Okay, so you got to know what the derivative of the arctangent is, or the inverse tangent. That's the one that goes like this. It's 1 over 1 plus x squared. That's what the derivative of that is. Now, that's just a derivative formula that we learned. No chain rule. If that was the inverse tangent of something other than x, then it would be a chain rule. Then the derivative of x to the third is going to be minus 3x to the second, like that. That's it. That's a pretty simple derivative if you know the formula. Okay? So the next thing is you want to ask yourself the question, is this derivative ever undefined? I want you to look carefully at this derivative and tell me if it's ever undefined. Okay, let's see, you're squaring x. Now you do have x in a denominator, but if you square x, what do you get? You get a positive, okay. X could be, if x was 0, you would have 1 plus 0, so that looks like that derivative is always defined. Okay, so f prime of x is always defined. So you don't have any places where the derivative is not defined. Does that make sense? Okay, if you didn't see that, you could set 1 plus x squared equals 0 and you get imaginary numbers. So that would tell you that that's not a problem. So what do you do next? You take the derivative and you set it equal to 0. So let's go ahead and write that down and see if we can solve this equation. So now it's going to be algebra background issues again. Now you could right now get a common denominator if you wanted to. Doesn't matter that much. So let's do this. How are you going to solve this equation, you think? Get rid of the fraction. There you go. Okay. Multiply both sides by 1 plus x squared. Okay, so what we're going to get when we do this then, of course, that's going to cancel out leaving 1. And then you got to distribute it to get 1 plus x squared times 3x squared equals 0. It looks like we got an equation that maybe we can solve from there. So again, this cancels, but then you're doing a distributive property, so you have 3x squared times 1 plus x squared. Okay, so let's multiply this out. So we have, and do this carefully, we're going to have minus 3x squared minus 3x to the 4th is equal to 0 like that. Okay? Now this one could get into some kind of interesting stuff here. Okay, does that look okay? Yep.
Aren't you supposed to plug in x minus x cubed at the original? Where it's 1 plus x squared, so should it be 1 plus x minus x cubed squared?
Well, this is, let's see, the original function had 2 parts, right? Inverse tangent of x minus x to the 3rd.
Yeah. Aren't you supposed to plug that in the x part in the 1 over 1 plus x squared?
Which part? Well, this the inverse tangent is just 1 over 1 plus x squared.
Oh, okay.
So it's just x.
Yeah, that x to the 3rd is separate from that inverse tangent. I think that's what you're thinking.
Yeah. Sorry.
Yeah, okay, that's okay. All right. So then that should be the derivative, and then we just need to simplify this. Now, what you're going to run into on some of these problems like this is if you were to go through and if you were going to multiply both sides by a negative here, and I'm going to do this just because it might make the factoring easier. So what we would have is we'd have negative 1 plus 3x squared plus 3x to the 4th equals 0. I'm not even sure if this thing will factor or not. It might. If not, we can just kind of look at the critical points in a graphing calculator if we want to. Okay, I'm not sure if that thing factors or not. I could try, so let's see, we'd have like 3x squared, x squared, 1 and 1, yeah, I didn't get a factor. I didn't think it was going to factor. So what I'm going to do in this case, so I've got my derivative done, and I'm going to set this equal to 0. One thing that you could do in this case, and you don't have a formula, you can't use a quadratic formula, you could do something that's called quadratic reducible. What I'm going to do in this case, I'm just going to show you how to do this with some technology. Sometimes equations are best solved with technology. So let me show you how I'm going to do that. So what I'm going to do is I'm going to take 3x to the 4th, like this, plus 3x to the 2nd, minus 1, and I'm going to graph that in the standard window. Now, if you go to college algebra, one thing that you would know, hopefully, is that if the degree of the polynomial is even, do you guys remember from college algebra that it does either this or it does this? Okay, so I know that. I also know the y-intercept's negative 1, so I know it's going to have to cross the x-axis somewhere, so I'm just going to put that in, standard window. Well, let's see if we can figure it out this way, okay? Now, for some reason, it's like stuck. It does that sometimes. Like I'm confusing the calculator or something. Try again. Okay, so let me try one more time, standard window. Let's see what happens. Okay, we should see 2 places where it has a 0. Okay, Now, one thing that you could do on this one is you have what's called a zero command. I'm going to zoom on this a little bit. I'm going to change my x values to like -3 to 3 and regraph it just so I'll see this a little bit better. And there's a 0 right there. Okay. Now, one thing that you can do is you can go like this. You can go second trace, and then you can press this 0 command, and you can get like a left and right bound. So if I want to get this left bound, that might be in there somewhere. Press your right cursor key to get a right bound. Okay, so there's a critical point that's going to come out right there, 0.51. Now that probably is an irrational number that you could have gotten with some other techniques. Well, let's just say that's 0.5. Since this graph is symmetrical, that derivative is symmetrical, it's an even function, that's going to be -0.51 also. So let's just say our critical points then are, round them off to about 0.51 and -0.51. Have you guys done that 0 thing before? Okay. You get into this occasionally if you can't solve this equation numerically, then you have to look at it more graphically. So then let's just kind of do a sign chart. Now, I'm not going to do a lot of the details of the arithmetic on this because I think I've done enough of that. But what you would basically do on your sign chart is you'd go like this then. So you would end up going, you have a critical point at x equals -0.51. Then you have a critical point at approximately x equals 0.51 like this. All right? And then what you're going to end up having on this, so if you did test points, like you could do something like -1 here, 0 here, 1 there. Now you would plug in to the derivative, and the derivative you could plug into this thing right here if you wanted to. And if you did that, what you would have, now let's just look at the graph and predict, because I want you guys to be able to do this. Okay, basically what is the derivative going to be when you're less than this critical point? Right there. Negative, okay. Okay, you can use your calculator to help you with that. The next critical point we have is there. So what's the derivative going to be from there to there? Positive, okay. And the derivative from here on out is going to be what? Negative. You guys see how the graph tells you the sign chart? That's good. I want you to know that. I want you to know that technology opens that up for you. You can do that. Save yourself some time. Now we can go through and we can write this out. Now this is a continuous function. So what you'd kind of end up having is you'd end up having a function decreases, hits a low point, increases, kind of does something like that. Okay, so that means that what we would have is we'd have a local min there, local max there, and then we could go through and get all the information we need. So we'd have a min at approximately -0.51. Then we'd have a maximum at approximately 0.51. Increasing would be from -0.51 to 0.51. Then decreasing is going to be -infinity until you reach that critical point. And then 0.51 to infinity like that. And that'll take care of it, okay? All right, so what do you guys think? What do you think's the hardest part of what I taught you today? Probably, what I find students have the hardest time with,